You can't go the other way. It's not possible, right? It would be like rolling up a hill when you have no energy to do so. So what we would say here is that if we tracked one little electron, we'd say, okay, it has 6 joules per coulomb, or 6 volts right there. It still has 6 volts right here because it hasn't used any yet, but then it goes through the resistor and it uses up that 6 volts of energy and it's left with 0. Really, it's actually a little bit that's not 0, just enough to get back here, but we assume that the wires have no resistance. Now the ammeter does not affect the current, because that would be dumb if the thing we were using to measure the current actually affected the current. Then we wouldn't know how to get accurate measurements of current. So in other words, anytime there's a resistor, there's a voltage drop. So let's look at a more complicated one. So here I have a battery, and I'm going to call this first resistor resistor 1. We'll do a resistor 2. And then I'll go ahead and I'll just put another one here, resistor 3. Now, what we would say is, let's make this a 9-volt battery. Okay, let's say that this point here, A, there is 9 volts right there. Here at B, we're still good. We still have 9 volts. We haven't used any. But now there's a drop in potential as we go through here. So let's say point C here, let's say I lost 3 volts worth. Okay, it's going to depend on the strength of this resistance. But let's say that now here I only have 6 volts, but so I'm still going to keep moving. I get here to D. D, I still have 6 volts. I haven't used any. Here I'm going to drop actually, and in this resistor here, when I get to E, maybe I'll only have 3 volts worth left. I get to point F, and I've still got 3 volts, and then I go through resistor 3, and there at point G, I'm back down to 0 volts, and then at point H on the other side of the battery, again, I have 0 volts. So you can see what's happening as you pass through a resistor is that you're using energy, so there's a voltage drop. So I'm going to write V for voltage. So there's a voltage drop. Now, the amount of voltage drop depends on different things, right? So we'll call the voltage drop a delta V, because it's a change, right? So that would be 9 minus 6, which would be a 3 volt drop. That depends on how resistive the resistor is. So if it's more resistive, it causes a greater voltage drop. And it's going to actually be determined by the amount of current. So in playing through the activity, you hopefully saw that when you made the voltage of the battery bigger, the current, remember I stands for current, also got bigger, right? Which makes a lot of sense. It's like if I'm a battery that can do more joules of energy per charge, or per coulomb, which is what a volt is, then I should be able to give more energy to the electrons, which would mean that the current is going to be stronger. So we would say that voltage is directly proportional to current. Then when you did your experiment where you changed the resistance, you saw that resistance was inversely proportional to current. In other words, as the resistance got bigger, the current dropped. Now that's of course if you're keeping the voltage constant, because you can't change more than one thing at a time. So if I were to look at this graph here between the voltage and the current, I got a direct relationship, and the slope of that graph is actually 1 over the resistance that you used, which is very interesting. Well, that's the thing that you held constant in your experiment, so it's the thing that should show up as the constant of the function. So let's take a look at that. As I made voltage bigger, the current got stronger. So we saw that that was true. And in the experiment, so I'm going to draw the corresponding circuit here on this side. Now, as a shorthand method, we use a little zigzag line to represent the resistor, and then we use a long line, short line parallel to each other to be the battery. So this is my battery. This is my resistor, and I'm only going to have one resistor. So basically what this experiment was is that if this gets stronger and stronger, then the current through the wires, sorry, I should draw from positive, which is the long one, to negative. The current is going to get stronger and stronger and stronger. But we kept the resistance constant the whole time. And the value of the resistance shows up as the inverse of the slope. So the slope is equal to 1 over the resistance. So if you're trying to figure out what the resistance is of a resistor, you just calculate the slope of that graph and then do 1 divided by that slope. Now this, if we were going to write an equation for this line, we would write y equals mx plus 0, so I'm going to leave that out, where y is the current, m is 1 over the resistance, and x is the voltage. Now, what I'm going to do is move some of these variables around. So let's look at this. Okay, all that this equation is saying is that when I increase the voltage, I increase the current. When I increase the resistance, keeping the voltage the same, I decrease the current, because they're inversely proportional. Now, it's more commonly seen this way. So I'm going to multiply by R on both sides. And what I'm left with is V equals I times R. And really it should be delta V. So this equation is used for everything in this unit, which makes it pretty easy. And it's oftentimes called Ohm's law. Now, a disclaimer. Ohm's law is a little bit more complex than that, but for our first level physics courses, we refer to that as Ohm's law. So here's how you can use it. Here's my battery, here's a resistor, here's another resistor, and we're back. Okay, let's say this is a 9-volt battery. Let's say that this resistance is 3 ohms, and this resistance is 3 ohms. And I might ask you, what is the total resistance in this circuit? Well, the total resistance turns out to be just the resistances of each one added together, so that would give me 6 ohms. Now if I wanted to find out the total current in this circuit, I would use the Ohm's law equation. Delta V equals I times R. Now I'm going to find the current. We know that the current has to be the same all the way throughout here because there's no place for it to have split up, right? So anywhere through this current, anywhere through the circuit, the current is the same number. So let me just calculate it right here, and then I'll see if it works in both places. So let's think of my voltage drops. I'm going to have a voltage drop over here, and I'm going to have a voltage drop over here to get back to 0, and they should be the same voltage drop because they're the same resistance. So half of 9 is 4.5, so there's a 4.5 volt drop over both resistors. So let's figure out what the current is. Now I could put the total resistance, so the total voltage is 9, the current and the total resistance is 6, so I should be equal to 9 over 6, which could be 3 over 2, and that is 1.5 amps. Now if I just calculated the voltage at just one place right here, right? I would use the same equation to figure out what the current is running through there, and you'll see it's the same. So the voltage drop is 4.5, the resistance is 3. So 4.5 divided by 3 gives me 1.5. And I'm going to check it on my calculator just to make sure. So 4.5 for the voltage divided by 3, and I'm left with 1.5. So I can see that even if I just calculate the resistance right here, or if I use the total values of the circuit, I get the same answer. Let's do one more practice question so that you feel a little bit more comfortable for the practice quiz. Alright, so let's say I draw a circuit, and I'm going to put 3 resistors in here, and I'm going to give them different resistance values. Let's say that this is 12 volts, the battery. Let's make this 4 ohms, 2 ohms, and 1 ohm. Okay. Now remember, the rule is the current has to be the same everywhere because charge is conserved, right? In other words, charge is not getting used up. When you go through the toll booth, you don't pay with your car, you pay with the energy. So the number of charges at any point are exactly the same. So let's say that we want to find the total resistance first. That is, I'm just going to add the resistances all together. So 4, 2, and 1. And that's going to give me 7 ohms as my total resistance. Now let's figure out the total current, which is the same at any point. The voltage is 12, so I'm not going to forget that. Alright, so I'm going to do, I want to use total voltage, or potential difference, is equal to I times R. And when I'm doing the total, I'm using total, and that will give me total. Okay, so the total voltage was 12. I'm looking for the total current. Total resistance was 7. So there you can see, just divide by 7 on both sides. And so the total current in the circuit is going to be just 12 divided by 7, which is 1.7 units of amps. Alright, now just to verify again, that 1.7 amps is going to be exactly the same at all locations, here and so on. So if I do the 1.7 amps, I can figure out the voltage drop over here at this location by just using the same old equation. So delta V equals I times R. So I plug in the I, which is 1.7. I plug in the R, which is 2. And right then and there, I can see that the voltage drop that's going to be over that 2 ohm resistor is going to be 3.4 volts. Because you can see they're not going to be all even voltage drops because they have different resistance amounts. But I can figure out every single one by saying I times R. So in this case, I is the same again, 1.7, but here it's times 4. Alright, so if we did 1.7 times 4, we would get 6.8 volts. That's how many volts drop or used up over the 4 ohm resistor. I should say transferred rather than used up. And over here at the 1, that would be 1.7 volts, right? Because I have 1.7 amps times 1 ohm. Now all 3 of those should add up to the same. So 6.8 plus 3.4 plus 1.7, and I get 11.9, and that's because I rounded. So the total voltage equals the voltage drops over each location. Okay, because you can't create or destroy energy. Now I know this video has a lot of information in it. That's why we've given you 2 days to work through both of these videos and those practice questions. So good luck, and review any parts that you need to again.